So we're going to start our study now of differential equations. Students have probably seen some differential equations before in a course like Math 122L here at Duke, possibly Math 112L. Some of the differential equations that you've seen before are things of this sort, and we won't review here how to solve those kinds of differential equations. We presume that you remember how those solutions work. Let me just remind you very quickly, though, that when we're solving a differential equation, we're not looking for a value of x that satisfies the equation. We're looking for a function, in this case y, that satisfies the equation for all values of x. So in this case, we're looking for a function whose derivative is this given function f of x. Here we're looking for a function whose derivative is a multiple of itself. Here we're looking for a function whose derivative relates to its values and the values of these other functions. So in particular, solving a differential equation is the search for a function that satisfies the equation for all values of x. So there's something we have to worry about when we say we're solving differential equations. For one thing, differential equations do not always have solutions. This is a problem. Certain conditions being satisfied, we can draw that conclusion, but in general, we can't. Furthermore, differential equations do not always have unique solutions. Now, students are mostly familiar with the idea of there being many solutions to a differential equation, but are under the impression that if you ascribe an initial condition, then there will subsequently be only one way to solve the equation. Usually what happens is in the process of solving the differential equation, you at some point find yourself taking an integral of something which turns into some expression plus c. And the initial condition allows you to solve for that c, which then gives you the solution. This, roughly speaking, what happens very often. The thing is, that does not always work. Sometimes, even with an initial condition, the solutions are still not necessarily unique. You still might have multiple solutions. So I'm going to show you an example of where this oddity can come up. And this is the kind of thing that we have to worry about in Math 216. So let's think about this differential equation. Now, you can see it coming that when you take an antiderivative, you separate, do the antiderivative, you're going to have an integration constant. And of course, that integration constant could be lots of different things. But now notice further, we are assigning an initial value that when x is equal to 0, the value of this function y that we're looking for also equal to 0, and it feels like there should then be a unique solution. Surely this would help us evaluate the integration constant or something along those lines. Here's the thing. This function right here, plug that in, it satisfies the differential equation. Furthermore, not hard to check, it satisfies our initial condition, and so we have here a solution to this initial value problem. However, this function here, plug it in, it satisfies the differential equation as well, and it also satisfies this initial condition. So what we have, disturbingly, is two separate and different solutions to the same initial value problem. And this is the type of thing that you probably did not see in a single variable calculus course. So, what do you do in a situation like this? Good news, we're not going to worry about that in Math 216. In Math 216, we're going to protect ourselves from this kind of worry with certain theorems, such as this one. And this is what I like to call the existence and uniqueness theorem for a certain category of differential equations. So here it goes. Suppose we have an initial value problem. There's an initial value problem. Note that means that there's a differential equation and an initial condition. Note that this differential equation is of a very specific form. This is not just some equation that involves a derivative in some way. This is a differential equation that says dy dx equals, so that's very specific, and then furthermore on the right hand side, some expression involving only x and y. So dy dx only on the left, and no dy dx's or anything of the sort on the right. So it's a very specific form. If the differential equation takes that very specific form, if this function is continuous, and if the partial derivative of that function with respect to y is continuous, if all those conditions are satisfied, then the initial value problem does have a unique solution. So the solution exists, and the solution is unique. Okay, so that's a wonderful theorem to have to work with that says with these certain conditions being satisfied, you don't have to worry about this sort of nonsense here. This sort of nonsense like this, where you have an initial value problem that has, in this case, two separate solutions. All right, so in Math216, we're going to primarily concern ourselves with differential equations that do satisfy the conditions of this theorem, and therefore to which we can apply this result. Okay. Some quick comments about techniques. The technique of separable differential equations, students have seen before in single variable calculus class. Notice that if it's separable, you can get all of the y's over to the left and all the x's over to the right, and you can integrate both sides and solve. So this should be an old idea. Students should review this and make sure they remember how to go about that. And then just a quick preview. There are some other techniques. We're not going to study these in detail in Math216, but you will see these next two techniques in the next course, Math 353. So some differential equations can be put into this form. Very special form, again. Got to fit exactly this form. And then certain key observations can be made, turn that into an equation, which you can then solve for the function y in question. Other differential equations should be put into this form, and if so, then there's this clever trick, which is multiply both sides of the equation by this expression, and then a key observation can be made that allows you to solve for the function in question. These will be studied in more detail in Math 353.